Hello everyone, and thanks for watching Edupedia World Videos. This is the third video in the chapter Electromagnetic Induction, and in this video we see what happens when we connect an inductor and a resistor in series. At the end of the chapter Capacitors, we saw what happens when we put capacitors and resistances in series, and those were called RC circuits. So similarly, what we'll be studying now is LR circuit, that involves inductor and a resistor in series, and once we get to the next chapter called alternating current, then we'll mix all three together and we'll see what happens in LCR circuits as well. Just a little bit of recap: if we have a solenoid that also behaves like an inductor, and the value of the induction, the self-inductance of the solenoid, is equal to mu naught n square pi r squared L. N is the number of turns per unit length, pi is obviously the universal constant, mu naught is the constant of permeability, r is the radius of the solenoid, L is the total length of the solenoid. We see that the self-inductance depends only on the geometrical factors of the solenoid. What this means, self-inductance, is that if there is a current I flowing through the solenoid, then the flux due to the magnetic field, I'll not write B because here we'll just be talking about magnetic fields, but the flux due to the magnetic field is proportional to the current, and the proportionality constant L is called the self-inductance, and that can be calculated to be this value. Right. Also, it means that the EMF, induced EMF, will be equal to minus L di by dt. So just like, let's say you have a resistor in a circuit and current is going in this direction, then once you go from this point to this point, we see a change in EMF of minus IR. If you go from the left to right, then the right is at a lower potential, so the potential difference decreases as we go from left to right. Similarly, as we'll move across an inductor, we'll attach an EMF of minus L di by dt. So let's begin with the simplest circuit, RL circuit. And both of them are connected to a battery. Let's say of EMF E. This is R, this is L. The current will obviously flow, positive current will flow out from the positive terminal of the battery, and it will go inside the negative terminal of the battery. So this is the direction of the current. What we'll do is, we'll apply KVL, Kirchhoff's voltage law, across this loop. That's the same thing we did with capacitors. So the equation will be, let's say we start at this point. From this point to this point, the EMF will rise by an amount E. Right? This E is not the EMF across the resistor or across the inductor. This EMF is the electromotive force of the battery, and that is the potential difference between these 2 points. We've studied batteries before as well. So going from this point to this point, an EMF rises by E. Going from this point to this point, it's 0 because these wires are conductors. This point to this point, the EMF decreases by an about IR. So minus IR. Similarly, going from this point to this point, it decreases by an amount L di by dt. And we know that this is equal to 0 because once we come back to this point, the voltage will be same. So we went throughout the loop and we wrote down the potential differences across each of them, and this is the equation we got. If this was a capacitor instead of an inductor, and we assume that this was a positive and negative plate, then instead of minus L di by dt, it would be minus Q by C, because that would be the potential difference across a capacitor. And later we'll join all three of them too in the next chapter. Right now this is our equation, and this seems like a simple enough equation to solve. We just need to do a little bit of mathematics. E minus IR is equal to L di by dt. So what I'll do is, I'll take dt towards this side and I'll take E minus IR towards this side, and I'll just, for the sake of it, take L towards this side as well. So this is the equation we get. We can integrate. If we attach the battery initially, then the initial current will be 0. Finally, let's say the current is I. Initially the time is 0. Finally, let's say the time is t. So the equation we get is t by L is equal to, and integrating this is a little tricky. It will be a logarithm, right? This is this whole term to the power minus 1. So it will be the log of this term, except I also has a coefficient of minus r. Right, you can do this by substitution as well, but I'm assuming you're fluent enough in integrations by now to be able to understand properly that this will be equal to minus 1 by r ln of E minus IR by E. Why by E? Because the upper limit is I, which gives us E minus IR. The lower limit is 0, which is the value of I, so it will give us E. Lower limit, upper limit. Minus 1 by R comes because minus R is the coefficient of I in this case. Right? So we'll just take R towards this side, take the minus towards this side, and then we'll take it to the power of E. So the equation we get is E minus IR by E is equal to E to the power minus RT by L. Right, E goes to this side, and from that we get is IR is equal to E 1 minus E to the power minus RT by L. So the final equation which I'll write down, I is equal to E by R times 1 minus E to the power minus RT by L. Okay. So this is the equation. At t is equal to 0, this particular value will be equal to 1 and the current will be 0. And that makes sense. Initially there is no current. Unless you just put a resistor, as long as you put some other thing, the current will increase finitely instead of being an infinite amount of current in a small time. Right, so initially the current is 0. After a long time, when we reach steady state, and this is the test for inductors. What is the test for capacitors? In steady state, there is no current going in this direction. In steady state, in inductors, it is not necessary that the current is not flowing, but the current is constant. That means di by dt is 0. So in the steady state, there will be a constant value of current. In that case, the EMF across the inductor will be 0, and we'll have our original R circuit, in which the current in the circuit will be IR. Current in the circuit will be E by R. Right. So this is the standard equation for the current, and the graph would go something like this. It will start from 0, and at infinity, it will reach the actual value. Right. The actual value would be E by R. Sorry, I don't think this will be the graph. My mistake. The graph will be like this, right? Because it has to be asymptotic, reaching the value of E by R, right? This is the I and this is time. Initially it will be 0, at time infinity it will be E by R. Now let's look at the other thing. When we look at an RC circuit attached to a battery, that was called charging of a capacitor, and then we looked at discharging of a capacitor, in which there was no battery, just a resistor and a capacitor connected. So in this case, let's say we have just a resistor and an inductor connected to each other. So the previous case was called growth of current, and this is called decay of current. Now, if you just leave this circuit as it is, then there will not be any current flowing because there is not any battery to drive the currents. So in this case, what we do is, there might have originally been a battery and then we remove the battery. So at t is equal to 0, that is our initial condition, there will be some current flowing through the circuit. How it's flowing is not our concern, but nothing is driving the current in this circuit. Right? So initially I will be the current, this is L, this is R, and again we'll get the similar relations. In this we'll get minus L di by dt minus IR is equal to 0. Right? From that we can get di by I is equal to minus R dt by L. From that we can get ln I by I naught. Initially the current was I naught. That's what we'll assume. So this is decay of current, where current constantly decreases. Earlier it was the growth of current, where current growed like this and eventually reached the value E by R. Right. So ln I by I naught is equal to minus RT by L. The limits in this integration, if you're wondering, are I naught to I and 0 to t, which gives me I is equal to I naught e to the power minus RT by L. Right. So this is basically decay of current, where current will flow like this. Initially it will have a value of E naught, it will keep decreasing, and at t is equal to infinity, the value will be 0. Right. By the way, this term and the previous term are sometimes written in the form of I is equal to I naught e to the power minus t by tau. Tau then is equal to L by R, and it is called the time constant. We saw a time constant RC when we were talking about RC circuits, that is a resistor and a capacitor. Here the time constant of the circuit is equal to L by R, and it has the same meaning as it did in capacitors. The time constant is the time in which 63% of the maximum current is reached if we are growing current, and 63% of the current has decayed if the current is being decayed. Right, that is one time constant in which the current decreases by an amount E. If T is equal to L by R, then at that time I will be equal to I naught by E, which is basically I naught decreased by around 63%. The final thing left in inductors is what is the energy stored in an inductor. We know the energy stored in a resistor, or the energy dissipated by a resistor rather, that is I square RT. We know the energy stored in a capacitor, that is half CV square. What is the energy stored in an inductor? So let's go back to our original equation in which we had an LR circuit. So this should be, let's say this is the smaller terminal, bigger terminal, E R I L. So the equation will be E minus IR minus L di by dt is equal to 0. This was what we started this video from, right? We can write it in a little bit different way. We can write it as E is equal to IR plus L di by dt. Now I'm going to use a little bit of trick which you'll might have a little trouble understanding the motivation for the trick. Where did I come up with that? But there are actually lengthier methods and more direct methods as well to find out the energy stored in an inductor. But this is a neat little trick, so I choose to do it by this method. Right? I'll just multiply both sides by I dt and then I'll integrate. Right? So what that will give me is integral of E I dt is equal to integral of I square R dt plus integral of L I d I, sorry, this should be dt, right? I'm multiplying both sides by I dt and integrating. So the first left hand side becomes E I dt. This side becomes IR multiplied by I dt, so I square R dt. This becomes dt and dt cancel, so I get L I di. Right? Now t obviously goes from 0 to t, 0 to t. I goes from, let's say, 0 to I. Initially the current was 0, or let's say I naught. So the equation we get is E I dt, that will give me E I t is equal to I square R t plus half L I square. Integral of I di will be I square by 2. Now what is IT? IT is the charge flowing through the battery, right? I is the current flowing, I into T is the charge. What is the charge multiplied by the EMF? That is the work done by the battery. We've seen that before. The work done by the battery is EMF multiplied by charge it sends out, because EMF is basically work done for a single unit charge. So this is work done by battery. This is I square RT is energy dissipated. Right, so the battery does some work. A part of that work will be dissipated as heat by the resistor, but the remaining part, half Li square, will be the energy stored in the inductor. Now the resistor dissipates energy, a capacitor stores an energy, and an inductor also stores some energy. So this is the final formula we have for this video. Energy stored in an inductor is equal to half Li square. Right. Just like the energy stored in the capacitor is equal to half CV square. Energy dissipated by a resistor is I square RT. Right. So this is the final formula. Now from this we can actually derive another very interesting result. What was the self-inductance of the solenoid that we began with? The self-inductance of the solenoid was mu naught n squared pi r squared L, right? And this is the solenoid, right? So we can see that pi r squared L is actually the volume of this solenoid, right? And we know that mu naught Ni is the magnetic field inside the solenoid. So the energy stored in the inductor was half Li squared. That can be written as half mu naught n squared pi r squared L I squared. That can be written as half mu naught squared n squared I squared by mu naught. I've just taken this mu naught n squared and I squared and I've added to mu naught. You'll see that why a second later. And then the left is pi r squared L, that is the volume of the solenoid. right? Mu naught Ni is the magnetic field in the solenoid. So from that we can get U is equal to half B square by mu naught V. V is the volume, E is the energy stored. From that we get the energy density, which is the energy per volume, is equal to B square by 2 mu naught. And this is an interesting result because it has an analog in electric field. When we saw capacitors, we saw the energy stored in a capacitor and we knew the volume of a capacitor, and from that we deduced the energy density due to the electric field, and that came out to be small u is used for energy density, capital U is generally used for energy. UE is the energy density of an electric field, that was half epsilon naught E square. UB, energy density due to magnetic field, is half mu naught is in the denominator, B square. And we see mu naught has sort of like the reciprocal of epsilon naught many different ways. In electric field we use 1 by 4 pi epsilon naught, whereas in magnetic field we use mu naught by 4 pi. So mu naught sort of behaves like the opposite of epsilon naught, E behaves like B, and then again during this whole unit of electricity and magnetism, we started out believing that electricity and magnetism are two different things. Electricity has to do with rubbing materials together, magnetism had to do with materials that pointed in a certain direction when you left them free, and so on. But as we analyze it further, now we ultimately see that electricity and magnetism, they are very much similar. Right, they have their own Gauss laws, they have their own flux laws in terms of magnetism. The energy density is very similar, all the formulas are quite similar. The inverse square law is common to both. So this is why electricity and magnetism are ultimately treated as part of the same thing, electromagnetism. Of course, the main reason for that came when we figured out that a changing electric field could produce a magnetic field. So this completes this chapter. Thank you.